So we're going to talk about the periodic table, periodic law, and I've given you your first official periodic table. Now I want to review a few terms. I want to make sure that we're straight. So first of all, periodicity, and this is something that you had in the video in the tutorial, but it's a tendency to recur at a regular interval. So we don't call these little blocks of time in which you have classes at school periods for nothing. They recur periodically. So at 9:20 every day we have third period. At 11:15, I think, 12:15, every day we have fifth period. It's a periodic recurrence. The seasons are periodic. The days of the week are periodic. Anything that recurs on a regular interval. When we talk about chemical periodicity, we're talking about the fact that if we organize the elements in order of increasing protons, there are characteristics that recur at regular intervals. So I just wanted to make sure we had that. Now, the other thing that I want to just refresh on, and I know you all know it, but is some terminology. So if we're talking about 1, 2, 3, 4, 5, 6, 7, that's n equals 1, n equals 2. These are main energy levels. So you have that from last chapter. If we're talking about a 3s, or a 5d, or a 4p, that's a subshell. That is multiple orbitals. If we're talking about 2px, or 3d1, or 4f2, 5pz, those are individual orbitals. So the big thing is I want you to remember the difference between subshells and orbitals. Okay? So when I ask you what subshell is filling, you better not tell me 3px, because that's not a subshell, that's an orbital. Okay, so I promised you a shortcut, right? You have been counting out stinking electrons. Jeez, oh, peas, oh, Moser, this is, bordering on abuse. Counting out electrons? Who does that? I told you that I would give you a shortcut so lightning fast, so magically efficient that you would be able to look at the periodic table and write the electron configuration. Not worrying about subshells, not worrying about anything, not counting electrons, nothing. You have it. Just like that. So, well, I guess I should give you the partial bad news. You know the whole ladder thing? The shortcut is also like a small ladder. It's like a kitchen step stool that you have to build on the side to get up to the next rung. So we're gonna build a little bit of that. So just a little side project we've got going, small kitchen step stool. It's okay, it won't take us but a minute. So I'd like you to look at that next slide, and I'd like you to read it to yourself for a moment. While you're doing that, I'm going to give you something else. You know what? I'm just going to take 12-ish and pass them down. So everybody should have about 12 of those little scraps of paper. I'll read that, it makes sense. Groups run vertically, groups run up and down. Years and years ago, a student of mine who was really good at making up memory tricks said, oh, gravity pulls things down. Groups run up and down. Okay, that works. And periods run across the table. They're horizontal. Now that second bullet point, is that real comprehensible, real clear? Length of periods is determined by number of electrons that can occupy sublevels being filled. Humph. So I would like you to take 2 of the little scraps of paper you've got, and on one of them I would like you to write the electron configuration for hydrogen, and on the next one I would like you to write the electron configuration for helium. Okay. These are the elements of the first period. Great. What sub-level or sub-shell or sub-shells are we filling here? 1s. How many electrons can 1s hold? Answer with your fingers. How many elements are there in this period? Huh. Peculiar. So now, I'd like you to take a bunch of those little slips of paper, and I would like you to write the electron configurations for lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. I ran right off the page. So write the electron, and you can do noble gas notation if you want to. What noble gas would you use for these? Helium. So you could start them all off with that. Once you've got all of those written out, tell you what, when you're done, stick your thumb on your forehead. What subshells are being filled? What subshells are being filled? So we've got S and P being filled, 8 electrons fit in an S and P, and there are 8 elements in the second period. Weird. So I'd like to draw your attention to the third period, the one that starts with sodium. Goes all the way across to argon. How many elements are there in that?
8.
Huh. What subshells do you suppose are being filled?
3s and 3p.
Really? 3s and a 3p. Yeah. So when we get down to the fourth period, the one that starts with potassium, how many elements are in the fourth period? 18. So we said 8 was an S and a P. Is there any subshell that would add 10? A D, because you have 5 d orbitals. They each hold 2 electrons. What do you suppose happens in that fourth period? We start filling a D. Huh. Well, that's odd. Peculiar. Okay, so does it now make sense when we say the length of the period is controlled by what subshells are being filled? So when we get down to the point where we have Fs, should the periods get longer? So you got 14 electrons in an F subshell? How's that going to work? We'll have to see. Okay, at this point I would invite you to do something. I would invite you to take your periodic table and I would invite you to label the periods. So the periods are 1, 2, 3, 4, 5, 6, 7. We only go down to 7. The lanthanides and actinides, you'll see why they don't get their, well, you'll see. It's part of the unfolding mystery. Okay, so we said period 1 we're filling, and you have to kind of ignore the fact that there's a second hydrogen on there. It's repeated because, well, you'll discover that too. And in the second period we're filling an S and a P, 2s and 2p to be specific. Third period we're filling an S and a P, 3s and 3p. Fourth period we add a d orbital, or a d subshell. Woo! You gotta be careful. Really gotta be careful. We add a d subshell. Okay. So at this point I would like you to take some of your cards, and you've already got lithium. I would like all of you to write the configuration for sodium, potassium, and rubidium. I would highly suggest that you do noble gas notation. So do you all have 3 more cards? So compare notes. See if either or both of you see any particular trends, anything that jumps out at you. One of the trends that you guys noticed is that in lithium, which is in the second period, what's the highest main occupied energy level in lithium? 2. In sodium, which is in the third period, what's the highest main occupied energy level? 3. And potassium, 4. And rubidium, 5. If you were a betting sort of person, what would you bet the highest main occupied energy level for cesium was? 6. So, as it turns out, highest main occupied energy level is always the same as the period. That's the first part of the kitchen step stool that we're building to get to the shortcut. So, whatever the period is, that is going to be the highest occupied main energy level. That's convenient. That's handy. So for any element on the periodic table, let's practice this. Germanium, atomic number 32, somebody with shoelaces. What's the highest occupied main energy level? Somebody with shoelaces. I got 1, 2, 3, right here. 4. Yeah, it's in the fourth period. It's going to be fourth main energy level. For lead, what's the highest occupied main energy level? PB, no lead in my peanut butter sandwich, number 82. 6. It's on the sixth period. Okay. This is a start. This is a start. Now I'm going to have you work in groups by row. And we're a small class, so it's going to take us a little bit longer. This first row, each of you will do one element now. So you all did beryllium. John, your magnesium. Raven, your calcium. Jacob, your strontium. Kiara, you are boron. Kaylee, your aluminum. And Claire, your gallium, atomic number 31. Rachel, your carbon. Ella, your silicone. And Ashlyn, your germanium, Ge. Skylar, oh wait, we did boron and carbon, huh? We already did those. So, indium, tin. Skylar, your phosphorus. Claire, Madison, your arsenic. And your antimony, Sam, SB. Okay, so just do the noble gas notation for your element, and then you're going to look at your whole row together. Let's go back to our periodic table here. I almost missed the, very nearly missed the stool. Okay. Okay, from the first of our brave herd, what trends do you notice in that second column, that second group?
They all end in S2.
Ah, Gesundheit. So these all end with a nice S2. And we said that this first one all ended with a what, S1? Okay, so let's go over to boron. Kiera and Kaylee and Claire. It's a nice little alliterative thing. What do you notice? Oh, so these all end with a P1, which means, of course, that they have an S2. What about you guys?
They all end with a P2.
Oh, so these all end with a P2, which of course means they also had an S2. What about this row? Ah, so they all have an S2 and a P3. And some of them, if we get down lower, have some D's in there too. And so some of you would have discovered that. Well, that's peculiar. I did the next row. I did silicone, selenium, and tellurium. And look at that. P4. Huh. So if this one is S2, P4, I ran out of space there, what do you suppose everything in this row ends with? Would you say what? S2P5? And what about these guys, the noble gases? Oh. Interesting. Interesting. So we now know that we can figure out the highest main energy level from the period. and the group will tell us what they end with. Are you seeing the shortcut in sight? Pardon? We're going to get there. We're going to get there. That's a fantastic question. We're going to come back to that. Well, let's see. Let's do it for atomic number 88. Can you write the noble gas notation quick, quick, quick? Radium. Okay.